Now we are interested in deriving an expression for EMF induced for distributed coils which are connected in series. So this particular uh, portion can be thought of as the continuation of the previous class. In our previous class, we have derived the expression for EMF induced in a single multi-turn coil. So now in this particular class, we are interested in finding an expression for EMF which is induced for distributed coils connected in series. Actually, it should be like this one: is that you have say two or three number of coils, and these two or three number of coils are connected in series, and further these two or three coils are distributed over the rotor periphery. So we wanted to know that what would be the expression of induced EMF for these series connected coils which are distributed over the rotor periphery. So let me take you to the concerned slide. So you can take this particular diagram. So what you can find in the diagram is that we had two coils which are named as 1 dash and 2 dash. So these two coils are connected in series. Further, you will note that these two coils are multi-turn coil. Although I have indicated two number of turns in the diagram, but in general, you can take this coil to be having n number of turns. So it's a multi-turn coil, and in the diagram right now, you can view that two coils which are named as 1 dash and 2 dash. These two coils are connected in series. Further, these two coils 1 dash and 2 dash, they are distributed over the rotor periphery. So if you can follow this mouse pointer, you can find here you are having coil side 2 here. So diametrically opposite would be the coil side 2 dash. Likewise, you are having coil side 1 here. You may follow the mouse pointer, please. So this is your coil side 1, and this is your coil side 1 dash, which is again diametrically opposite. So you can view that along the rotor surface or along the rotor periphery, these two coils are distributed over the rotor periphery. And yes, these two coils are multi-turn coils. Although in the diagram I have indicated the coils having double turn or two number of turns, but in general, if it is n turn coil, in that case, in each coil side, you will have n number of conductors. For n turn coil, you will have n number of conductors on each coil side. So let us make some recapitulation so that it's easier for our understanding. Is that on the right hand side you can view that variation of B means the magnetic flux density along the air gap periphery is indicated. So what you can view that the space distribution of magnetic flux density along the air gap periphery is sinusoidal in nature. That means let us think of some sort of hypothetical experiment where in that hypothetical experiment we are measuring the strength of magnetic flux density. Say we are measuring the strength of the magnetic flux density in the air gap which is at theta mechanical equals to 0 degree. So we have started with a point in the air gap periphery. We have started with a point in the air gap periphery which is lying on the axis, which is falling on the axis theta mechanical equal to 0 degree. So we have chosen a point at theta mechanical equal to 0 degree, and we have measured the strength of the magnetic flux density, that is V. Then measuring the magnetic flux density in the air gap for different points along the air gap periphery. That means, let's say we are measuring for theta mechanical equals to 30 degree, then we are measuring for theta mechanical equals to 60 degree, then we are measuring for theta mechanical equals to 90 degree, then we are measuring for theta mechanical equals to 120 degree. In this way, we have measured the value of the magnetic flux density along the air gap periphery. And after measuring the value of the magnetic flux density along the air gap periphery, we have drawn it on a graph where along the y-axis we would be writing the strength of the magnetic flux density, and along x-axis we would be writing the value of theta mechanical, because with the value of theta mechanical you can locate or you can pinpoint any point in the air gap periphery with accuracy. That means, let's say, you may follow the mouse pointer please. If say you want to have this particular point, so this particular point will be defined by theta mechanical equals to 90 degree. Likewise, this particular point, please follow the mouse pointer, this particular point would be identified by theta mechanical equals to 180 degree, isn't it? So with the help of this theta mechanical degree, it is possible to have a exact location of the point in the air gap periphery with the value of theta mechanical. Now, if you think in a deeper way, then you would get to know that actually the thing is that it's not sinusoidal to be true. It's not sinusoidal. Actually, it is your rectangular in nature or trapezoidal in nature, depending upon the coils which are distributed over the stator core periphery. I mean to say this one. Let us move to the previous diagram. Like this one. If you have a single coil on the stator core, then that single coil will have a mmf distribution which is like this. But this thing is replaced by Fourier series expansion. So we are expressing this as a summation of fundamental component and other harmonic components. We are neglecting the harmonic components. So that's why we are saying that the distribution of mmf along the air gap periphery or the distribution of magnetic flux density along the air gap periphery is sinusoidal. If you have more than one coils distributed over the stator core like this one, if you have more than one coils over the stator core which are distributed, then you will have this kind of waveform which is very near to sinusoidal compared to the previous case. Compared to this rectangular mmf wave, this waveform, that is the trapezoidal waveform, is more nearer to sinusoidal wave. So on that basis only, we are saying that we have made that assumption that we are ignoring the harmonic component, that is we are ignoring the space harmonic. We are only considering the fundamental component of flux distribution, and that is sinusoidal. So with the help of this theta mechanical, it is possible for us to locate any point along the air gap periphery. Depending on the value of the theta mechanical, you can uh, depending upon the value of the theta mechanical, you can locate any point in the air gap periphery. Now, what is the expression for induced EMF in a conductor? What is the expression for induced EMF in a conductor which is moving at uniform speed v, and it is in a flux density where value is capital B? It's your BLV. So EMF induced in a conductor which is having length L and it's moving with velocity v in a magnetic flux density B is given by BLV. So similar sort of thing is happening in this case. What you can find is that this coil can be viewed as set of conductors. For example, if it is a n turn coil, then n number of conductors is on this coil side, and you have n number of conductors on this coil side. So this n number of conductors, what is the value of EMF induced for this n number of conductors? It's given by N into BLV, where BLV the EMF induced in each conductor. Now whatever is happening to one conductor, that should happen to other conductors also. So the EMF induced on the coil side will be BLV. Of course the magnitude would be N into BLV, because if it is a N turn coil, then there would be N number of conductors, so it would become N BLV. But if you just go by the expression for EMF induced for a single coil, it is BLV. Now, between this, out of this BLV, L is the length of the conductor, which is constant, and we are assuming that the rotor is driven at a uniform angular speed. That means the revolution per minute, that is RPS or RPM, whatever you call, revolution per minute is RPM, and revolution per second is RPS. So if the speed of the rotor, mechanical speed of the rotor is uniform, it is maintained constant, then the peripheral velocity V would be constant. So if L and V are constant, then what is remaining? Only B, that is the magnetic flux density. So what the thing is boiling down to? The thing is boiling down to that whatever is the variation of B means the magnetic flux density, that would be the variation of the induced EMF through the coil. That means if the variation of the magnetic flux density, if the variation of the magnetic flux density along the air gap periphery is sinusoidal, so a conductor which is placed on the rotor surface, a conductor which is placed on the rotor periphery would see variation of flux density which is sinusoidal in nature. Why? Because in the beginning itself we have seen that the space distribution of magnetic flux density along the air gap periphery is sinusoidal in nature. So that is the reason that conductor which is placed on the rotor surface, conductor which is placed on the rotor periphery would see sinusoidal variation of the flux density as the rotor is moving. That means as the conductor is moving along the air gap periphery. Now, we have actually chosen a convention here that flux under the north pole would be treated as positive and flux under the south pole would be treated as negative. So that is why corresponding to theta mechanical equals to 90 degree, which is the center of the north pole, the flux density is having positive peak, and likewise corresponding to theta mechanical equals to 270 degree, you are having the center of the south pole, and that is corresponding to negative maximum for magnetic flux density, because we have adopted a convention by which flux density under the north pole developed on the stator core would be treated as positive, and flux density under the south pole would be treated as negative. So that's why for theta mechanical equals to 270 degree, you are having a negative maximum because it is corresponding to this point. Theta mechanical equals to 270 degree, which is the center of the south pole. And for theta mechanical equals to 90 degree, you are having a point which is under the center of the north pole. And as per the convention we have adopted, flux under the north pole of the stator core would be treated as positive. So theta mechanical is your positive max, I mean to say flux density B is positive maximum at theta mechanical equals to 90 degree. Now we have seen just now that EMF induced in the conductor is given by BLV. L and V are constant. So whatever is the nature of variation of B, that is magnetic flux density, that would be the nature of induced EMF. Since the variation of the induced EMF is sinusoidal, because the variation of B is sinusoidal, variation of B, that is magnetic flux density, is sinusoidal. That is why induced EMF is also sinusoidal, because induced EMF is given by BLV. L and V are constant. L is constant, V is constant. L is the length of the conductor, V is the velocity or the peripheral velocity of the rotor. So these are constant. So the EMF induced in the coil sides would be same as that of the variation of magnetic flux density B. So this is the variation of EMF induced in the coil. Now we would like to represent the EMF induced in the coil by phasor. Why we want to represent it by phasor? Because the EMF induced in the coils are sinusoidally changing with time, they are sinusoidally varying with time. So that's why the EMF induced in the coil can be represented by a phasor, because you know phasor is a quantity which changes sinusoidally with time. Phasor is a quantity which changes in magnitude sinusoidally with time. So EMF induced in the coils are sinusoidal because the nature of space distribution of B, that is magnetic flux density, is sinusoidal. So that's why EMF induced in the coil is also sinusoidal. So we are able to represent the EMF induced in the coil by phasor, because EMF induced in the coil is changing sinusoidally. Why EMF induced in the coil? Why EMF induced in the coil is changing sinusoidally? Because the distribution of B, that is space distribution of magnetic flux density, is sinusoidal. So that's why EMF induced in the coil is also sinusoidal. So we have represented the EMF induced in coil 11 dash by E11 dash, and we have represented the EMF induced in coil 22 dash by E22 dash. So now the question is that can we simply add the voltage induced in coil 11 dash and coil 22 dash? Let's say for example, if the EMF induced in coil 11 dash is 10 volt, that means what? On coil side 1 you have 5 volt, on coil side 1 dash you have 5 volt. So if you take the algebraic sum over this coil, you will see that the 5 volt on coil side 1 and 5 volt on coil side 1 dash, they are getting added up. So you have got 10 volts as the EMF induced in the coil 1 dash. We are saying it for example 10 volt. Similarly, coil 2 dash will have induced EMF 10 volts. So at first glance, it might appear that since the coils are connected in series, so we can treat the coils as source of EMF, because EMF is induced in the coil side. Since EMF is induced in the coil side, we can treat the coils as voltage source or EMF source, and we have learned that voltage source in series are added up. But over here, that thing may not work, or rather it is not going to work. Why it is not going to work? What I mean to say is that by that logic, that EMF induced in the coil would be added up, because the coil 11 dash and coil 22 dash are connected in series. That thing is not going to happen here. Why? Because the EMF induced in coil 11 dash, let us say it is 10 volt. So EMF induced in coil 22 dash is also 10 volt, but they are not in same phase. They are not in same phase. Rather, they are phase shifted. That means what? There is a phase shift between the induced EMF in coil 11 dash and coil 22 dash. There is a phase shift. So over here I have indicated a sinusoidal wave to be the nature of EMF induced in the coil. But if you draw the EMF induced in coil 11 dash, it will come as sinusoidal, right? Correct. If you draw the EMF induced in coil 22 dash, it will also come as sinusoidal, but it will be phase shifted. That means the sine wave, the sinusoidal voltage waveform, the sinusoidal voltage waveform for coil 11 dash and sinusoidal voltage waveform for coil 22 dash, they will be phase shifted by each other. So what would be the phase shift? The phase shift would be the angle which is expressed in electrical degree, strictly the angle which is expressed in electrical degree. What kind of angle? The angle by which the rotor should rotate, so that the peak of coil 22 dash is going to happen after the peak of coil 11 dash has happened. For example, let's say that if coil side 1 is under the center of the north pole and coil side 1 dash is under the center of the south pole, then EMF induced in coil 11 dash is maximum. But again, you will find that if coil side 1 dash, if coil side 1 dash is under the center of north pole and coil side 1 is under the center of south pole, that will also imply EMF induced is maximum. So the convention which we have adopted, that flux under the north pole is positive and flux under the south pole is negative. So in line with that convention which we have adopted in this particular analysis, we will say that if coil side 1 is under the center of north pole and coil side 1 dash is under the center of south pole, EMF induced in coil 11 dash would be positive maximum. And if coil side 1 dash is under the center of north pole and coil side 1 is under the center of south pole, that would be negative maximum. So now let us find out that what is the time instant for which the peak of the induced EMF, I mean to say the positive peak of the induced EMF in coil 1 dash would happen when coil 1 dash is coming in such a position, because the rotor is rotating. So in this particular diagram or snapshot, coil side 1 is not under the center of north pole. Coil side 1 dash is not under the center of south pole. But since the rotor is rotating in clockwise direction, at some point of time, coil side 1 would be under the center of north pole and coil side 1 dash would be under the center of south pole. So what will happen? Peak of the induced EMF will happen in the coil side 1 dash, positive peak. And after further gamma degree of rotation, coil side 2 will be coming under the north pole center and coil side 2 dash will be coming under the south pole center, gamma degree rotation of the rotor. So what is this gamma? This gamma is the angle between the center of the slot which is housing coil side 1 and center of the slot which is housing coil side 2. Let me again repeat it, that gamma is the angle between a line between those two lines. Gamma is the angle between those two lines which is drawn from center of the slot containing coil side 1 and center of the slot containing coil side 2. So that angle gamma is known as slot angular pitch. So if the rotor rotates by that angle gamma degree, which is termed as the slot angular pitch, then the positive maximum of coil 2 dash will happen after it has happened for 1 dash. So we say that the positive maximum or the peak of the induced EMF, the positive peak of the induced EMF in coil 1 dash and in coil 2 dash are not gonna happen at the same time. Let me tell this phrase particularly, it's very important. The positive peak of the induced EMF in coil 1 dash and the positive peak of the induced EMF in coil 2 dash will not happen at the same time. Rather, they are staggered in time. First, the positive peak of coil 1 dash would happen. That means coil side 1 would be under the center of north pole, coil side 1 dash would be under the center of south pole. So positive maximum of coil 1 dash is happening. After that the rotor will rotate. By angle gamma degree. Then coil side 2 would come under the center of north pole and coil side 2 dash would come under the center of south pole. After the gamma degree rotation of the rotor in clockwise direction, coil side 2 would be coming under the north pole center, coil side 2 dash would be coming under the south pole center. This is from the instant when coil side 1 dash had already in that position. Coil side 1 under north pole center, coil side 1 dash under south pole position. So we say that the peak of the induced EMF, the positive peak of the induced EMF for coil side 1 dash and 2 dash, they are not happening at the same time. Rather, they are staggered in time. What is the time difference? What is the time difference between the maxima or the positive maximum of induced EMF for coil 1 dash and positive maximum of induced EMF for coil 2 dash? So if somebody wants to know exactly how much time lag is there, between the positive maximum of induced EMF for coil 1 dash and coil 2 dash, the answer is the time taken by the rotor, to move by an angular distance of gamma degree, That time is the time difference between the positive peak of coil 1 dash and positive peak of coil 2 dash. So since the EMF induced in the two coils 1 dash 2 dash, they are not in same phase, rather they are phase shifted by angle gamma. That's why we are not allowed to take the arithmetic sum. We need to take the phasor sum. So E11 dash and E22 dash are drawn as phasor. Phasor OA represents the EMF induced in coil 1 dash. Phasor OA represents the EMF induced in coil 1 dash. Phasor OB represents the EMF induced in coil 2 dash. And the phasor sum of that is OC. So the voltage between these two terminals, the voltage between these two terminals would be given by OC. This the voltage between these two terminals would be given by OC. That is the phasor OC which is shown here. This one. This voltage, this thing would be given by this. Okay. So this was the case for two coils connected in series, and of course those two coils are distributed over the rotor periphery. Now one more important point is that we are having very less difficult time in this particular case, because here the number of poles are 2. That means if the number of poles are 2, if the number of poles are 2, then you can say that electrical degree and mechanical degree are one and the same. So that's why we don't have any problem. Now let us take the case where we have two coils connected in series, but it is for 4 pole case. So this is the case for 4 pole. So in 4 pole case, it is very important to keep in mind that electrical degree and mechanical degree are not same. So since electrical and mechanical degree are different, so what is going to happen in this particular case? You can just view over here. You can just view over here that this is your coil side 1, this is your coil side 1 dash, this is coil side 2, this is coil side 2 dash. So what you can figure out that the span of the coil 1 dash over the rotor periphery, or span of the coil 2 dash over the rotor periphery, is not 180 degree, rather it is 90 degree. If you compare with this particular case, over here what do you find? That these two coil side 1 dash, these two coil side 1 dash, they are placed diametrically opposite. So the span of the coil is 180 degree electrical, isn't it? You can just have a look here. This is your coil side 1 and this is your coil side 1 dash. So what is the span of the coil? Span of the coil is 180 degree. This is your mechanical degree. Okay, this is your 180 degree mechanical. So in case of two pole case, you are having two coils which are diametrically opposite. But in case of 4 pole case, you are having a span which is not 180 degree, rather it is 90 degree, and it has to be 90 degree. Why? Because when we are talking about full pitch coil means a coil whose span is 180 degree electrical. But if the mechanical span has to be found out, then you have to write theta mechanical equals to 2 by 2 into theta electrical. So if coil is full pitch coil, then if the coil is a full pitch coil, then theta is 180 degree. I mean to say the electrical degree is 180. So theta is 180. Theta mechanical we want to find, and P is the number of poles, that is 4. So you use the relation theta equals to P by 2 theta mechanical, this particular relation you use. Let me indicate it. This particular relation, theta equals to P by 2 theta mechanical. So if you put P equals to 4 and if you put theta equals to 180 degree, because it's a full pitch coil, then theta mechanical will come as 90 degree. So that is what is happening. The span between coil side 1 and 1 dash, the span between coil side 1 and 1 dash is 90 degree. Likewise, the span between coil side 2 and 2 dash is again 90 degree. Now, in this particular case, we should think one point very clearly, is that the angle between the line which is passing through the center of the slot 1 and center of the slot 2 is not gamma, it's actually gamma by 2, because it's a 4 pole machine. So for 4 pole machine, this relationship is valid, theta equals to P by 2 theta mechanical. So over here you can see that the phase difference between the induced EMF in the two coils, that is 1 dash and 2 dash, is indicated by gamma, no doubt. But if you think of the degree, I mean to say, if you want to find the mechanical degree, if you want to find the mechanical degree, that means what kind of mechanical degree I am talking about? I am talking about the slot angular pitch in mechanical degree. What is slot angular pitch? The angle subtended by one slot pitch at the center. So what you do, you draw a line from the center of the slot 2 and you draw another line from the center of the slot 1. So the angle between these two lines, the center of the slot 1 and center of the slot 2, so that angle is your slot angular pitch gamma. So this angle is a slot angular pitch gamma. So this gamma should be in terms, if you want to write in terms of mechanical degree, if you want to write in terms of mechanical degree, it won't be gamma, it would be gamma by 2. Then only in the phasor diagram it should be coming as gamma only. Okay, so the angle, the slot angular pitch in mechanical degree is gamma by 2. Gamma by 2, that means if you draw a line from the center of the slot containing coil side 2, you draw another line from the center of the slot containing coil side 1. So the angle between them should be gamma by 2. As far as the rotor periphery is concerned, as far as the mechanical degree is concerned for the slot angular pitch. But if you want to express the slot angular pitch in electrical degree, it would become gamma only, because it's a 4-pole machine. Now, as usual, the explanation which was given in the previous slide, here also we are assuming that the distribution of B along the air gap periphery is sinusoidal. That means if you choose a point over here in this point of this part of the air gap, this is theta mechanical equals to 0 degree. This is theta mechanical equals to 90 degree. This is theta mechanical equals to 180 degree, like that. So if you draw the distribution of magnetic flux density as a function of space angle theta mechanical, or simply plot the variation of the magnetic flux density, simply plot the variation of the magnetic flux density B along the air gap periphery, it would be sinusoidal. We are assuming it to be sinusoidal, rather we are assuming it to be sinusoidal by ignoring the space harmonics, and thus the induced EMF nature would be also sinusoidal, because EMF induced in a conductor E is given by the expression BLV. So BLV. So what is V? V is the peripheral velocity of the rotor, L is the length of the conductor, and B is the magnetic flux density. So B is changing in a sinusoidal way. So since B is changing in a sinusoidal way, that's why the induced EMF E is also changing in a sinusoidal way. Okay. So since the induced EMF is changing in a sinusoidal way, so we can represent the induced EMF in coil 11 dash and coil 22 dash as phasor. So we are representing E11 dash and E22 dash as phasor, and the phasor sum OC is the EMF induced across these two ends of the coil. That means the EMF induced across these two coil terminals, which are connected in series, but these two coils are distributed over the rotor periphery, would be given by this particular phasor. Okay, that is OC. So again we are taking the phasor sum. So what difference you have found out with respect to two-pole case? The only difference with respect to this two-pole case is the angle between the center of the two slots is gamma by 2 instead of gamma, because it's a 4-pole machine. So let us move to the case where you have got 3 coils in series. So over here we have got 3 coils connected in series, 11 dash, 22 dash, 33 dash. So in this particular case also we will find that the peak of the induced EMF in the coil 11 dash, coil 22 dash and coil 33 dash will not happen at the same time, rather it will be staggered in time. That means first the peak of the EMF induced, first the positive peak of EMF induced in coil 11 dash will happen, then gamma degree later, I mean to say the rotor, when the rotor moves by an angle of gamma degree, then the positive peak of coil 22 dash will happen. After that, further the rotor moves by gamma degree, further the rotor moves by gamma degree, then the positive peak for coil 33 dash would happen. So the positive peak of the coil 11 dash, 22 dash, 33 dash, they are not happening at the same time, rather they are separated in time or separated by angle, which is known as your slot angular pitch gamma. So this slot angular pitch gamma can be also thought of in another way, is that the time which is taken by the rotor to move by gamma degree. But yes, you should think over here that this being a two-pole machine, theta electrical and mechanical are same. I could not say the same thing for this particular case. Why? Because over here the number of poles are 4. So that's why the span in mechanical degree has changed compared to the two-pole case. This is a two-pole case. So here theta electrical and mechanical are same. So there is no problem in that. But this being a 4-pole machine, the slot angular pitch, that is gamma, in terms of mechanical degree, or simply you think that what is the angle between the center of the slot, which is housing coil side 2, and center of the slot which is housing coil side 1, that angle should not be gamma, it should be gamma by 2, because it's a 4 pole machine. So in this particular case, I will say that first the positive peak of coil 1 1 dash would happen. First the positive peak of coil 1 1 dash would happen, and after the rotor is rotating by gamma by 2 degree, rotor is rotating by gamma by 2 degree. After the rotor is rotating by gamma by 2 degree, what will happen? The positive peak of coil 2 2 dash would happen. So that is the particular difference you will have in this 4 pole case. In case of 2 pole machine, I was saying that the positive peak of coil 1 1 dash has happened, and after that rotor will rotate by gamma degree, so positive peak of coil 2 2 dash will happen. But in case of 4 pole machine, I have to say that after the positive peak of coil 1 1 dash has happened, the rotor should rotate by an angle of gamma by 2 degree, so that the positive peak of coil 2 2 dash would happen. So in this particular case also, since the three coils 1 1 dash 2 2 dash and 3 3 dash, they are distributed over the rotor periphery. However, they are connected in series, so their EMF will be added, but the addition of the EMF cannot be arithmetic. We have to take the phasor addition. So this particular word is the important word, that we have to take the phasor addition of the EMF which is induced in the three coils. We have to take phasor addition for these three coils, not the arithmetic sum. So AB is the EMF induced in coil 1 1 dash, BC is the EMF induced in coil 2 2 dash, CD is the EMF induced in coil 3 3 dash, and the phasor sum of that these three coils is AD. So AD is the phasor sum of the EMF induced for the three coils. Why we are not allowed to take the arithmetic sum? Why we have to take the phasor sum? Because the peak of the three coil 1 1 dash, 3 3 dash and 2 2 dash, the peak of these three coils, I mean to say the peak of the induced EMF for these three coils, they are not happening in same time. Rather, they are separated in time by gamma degree. That means between this AB extended and BC, there should be gamma degree phase difference. Likewise, between BC extended and CD, there should be gamma degree. That is the difference. So this was for your 2 pole case. This is for your 4 pole case. So all the things will be same. There won't be much difference except for one difference. What is that? That the angle, the slot angular pitch in mechanical degree, the slot angular pitch in mechanical degree would be gamma by 2. That means if you draw a line from the center of the slot 1 and center of the slot 2, then the angle between them should be gamma by 2, because it is a 4 pole machine. So in this case also you have got three coils in series. So again you have to take the phasor sum. So AB is the EMF induced in coil 1 1 dash, BC is the EMF induced in coil 2 2 dash, and CD is the EMF induced in coil 3 3 dash. So what is the EMF induced across the coil? These terminals, the EMF induced across these terminals is nothing but AD. So AD is the EMF induced across these terminals. So in this particular way, we can find the EMF induced across the series connected coils which are distributed over the rotor periphery or stator periphery. So now what has to be done? You must recall that we have derived a term which was defined as distribution factor, KD. So what is distribution factor? Distribution factor KD is the ratio of phasor sum by arithmetic sum. So it is the ratio of, we have to take the phasor sum divided by arithmetic sum, isn't it? So if you take this thing KD as the phasor sum by arithmetic sum, then we can simply do what is that we find the EMF induced in this one particular coil. Let's say EMF induced in this particular coil is E coil. So what is E coil? E coil is the EMF induced in coil 1 1 dash. Now what is the number of coils connected in series? Number of coils connected in series is 3. So we multiply by 3. So this is our arithmetic sum. But we have to take the phasor sum. So if you take this particular equation, what do you find? That arithmetic sum into KD is your phasor sum. So you multiply this thing by KD. That means the distribution factor. So you get the EMF induced in the series connected coils which are distributed over the stator periphery or rotor periphery. So we have already derived the expression for EMF induced in a single coil. What is that? Let me show you. This was the EMF induced for a single coil. That means for one single coil, this is the expression for EMF induced. So this is our expression for EMF induced for a single coil. You multiply this by number of coils connected in series, and then again you multiply by distribution factor Kd. So this should be multiplied by number of coils connected in series. Let's say it is NPH. So NPH is the number of coils which are connected in series, and again we have to multiply this by distribution factor, that is Kd. So what is Kd? Kd is the distribution factor. Why? Because we have learned that distribution factor Kd is nothing but the ratio of phasor sum of EMF by arithmetic sum of EMF. So you have got three coils here. So EMF induced in one coil is E coil, and the three coils are connected in series. You multiply by 3, you get the arithmetic sum. So I have got the arithmetic sum. Multiply this by Kd, the distribution factor, I will get the phasor sum. So the bottom line is that if you have series connected coils, the bottom line is that if you have series connected coil, then EMF induced for that series connected coil would be the arithmetic sum of the EMF induced for the coils multiplied by distribution factor Kd. Or simply saying, you just write down, just take the phasor sum of the EMF induced for those two coils or three coils which are connected in series and distributed over the rotor periphery or distributed over the stator periphery. So either you just find the phasor sum of the EMF induced in the series connected coils which are distributed over rotor periphery or stator periphery, or that is similar to saying that you multiply the arithmetic sum of the coil EMF by the distribution factor Kd. If you multiply the arithmetic sum of the coil EMF by the distribution factor Kd, you will get the phasor sum only. So in this way we can calculate the EMF induced in a series connected coils which are distributed over your space. Distributed over space means distributed over the rotor periphery or stator periphery. Now if the coils are short pitched also, in that case you have to multiply this thing further by Kp. If the coils are short pitched also, let's say the coil is short pitched also, so in that case you multiply the phasor sum, that means the arithmetic sum into distribution factor along with Kp. Kp is the pitch factor. This Kp is the pitch factor means what? It gives an indication about the reduction in induced EMF if a coil is short pitched. That means if this is your coil, so usually the coil is having a span which is 180 degree electrical. But if the span of the coil is less than 180 degree electrical, in that case you will have to multiply the EMF induced in the coil by Kp, that is the pitch factor. So in general, this product of Kp and Kd, product of Kp, that is the pitch factor, and Kd, that is the distribution factor, these two things will come into picture if you have a number of coils connected in series but they are distributed over the rotor periphery or stator periphery. There you will have this particular term Kw, that is the winding factor. So winding factor Kw is nothing but Kp into Kd. Kp is the pitch factor and Kd is the distribution factor. Of course, if you have full pitch coils and those full pitch coils are distributed over the rotor periphery or stator periphery, in that case Kp will be 1, so Kw is simply Kd only. This Kp will come into the picture if the coils are short pitched. If you have full pitch coils, in that case, if you have full pitch coil, in that case Kp is 1. So Kw, that is winding factor, equals to Kd only. So then this particular thing will do that arithmetic sum of the coil EMF multiplied by the distribution factor Kd. Okay, so let me stop over here for today. All of you, thank you for joining with me.